this video, we're going to talk about chemical compounds and bonding, and that's going to be a big focus of this unit. So this is kind of like the intro to these concepts. So we talked about compounds way back in Unit 1 last semester. So do you recall what they are? So they are pure substances, or a compound is a pure substance that is made of two or more atoms from the same or different elements. So we can see here we have two oxygen atoms bonded together, or here we have two hydrogen atoms bonded to an oxygen, also known as H2O. Notice how here there's sharing of electrons. That's going to be important later on. Here we see some silver atoms all bonded together, and those electrons being distributed around. We're going to talk about metallic bonding towards the end of the unit here. And here we have a salt crystal of sodium chloride, where we see that they're sticking together because of those difference in charges. We're going to spend a lot of time on ionic compounds this unit, and then we have a brief lecture on metallic, and a brief lecture, not really a brief lecture, a whole class lecture on covalent, and then whole next unit we'll spend on covalent compounds as well. Okay, so why do they form? Why are compounds forming? They're doing this by either exchanging or sharing electrons. So I could point out with, what was it? Oxygen and water, those were sharing electrons. With ionic compounds, we're going to see that they exchange electrons. And they're doing this so that they become more stable. And that's what we see here. When the hydrogen atoms aren't by each other, they're at a higher energy, but when they're bonded, they're at a lower energy. And remember, everything wants to go to its lower energy state. Do you recall what law this is? This is the second law of thermodynamics. We talked about that back in the periodic trends unit. All right. So with chemical compounds, we're going to be using chemical formulas. So I want to go over how to read those. So we're just going to use some generic one here. There's no meaning behind the letters beyond like what I refer to them here. So A and B here are referring to the elements involved. And then those subscript letters, by subscript I mean like if this is the normal line of script, right, they're below that normal line of script. Those are the numbers that represent how many of that element there are in the compound. So we would have X amount of A and Y amount of B. Unless it's in parentheses, so say I had like A, B, and then X. So if I have it in parentheses, that means I have X amount of A and X amount of B. But only in parentheses does the number distribute. So just like in math. So a few examples here. Let's say we have sodium chloride, NaCl. That means we have one sodium and one chlorine atom. C2H6. There's 2 carbon atoms and 6 hydrogen atoms. Al3+. Now this is an ion. So notice how the number is in the upper corner instead of in subscripts, right? This is that's in superscript, not subscript. So when we see it in the upper corner, that tells us the charge, not how many atoms there are. Formatting is super important in chemistry. It's why I'm a huge stickler for like the capitalization things, because if we have, so say you're dealing with like NO versus NO, NO here, with them both being capitalized, that's nitrogen and oxygen. Capital N lowercase o is nobelium. So very different things. All right, so with chemical compounds, we are going to be utilizing the mole again. The mole, if you recall, this is a way for us to talk about the number of atoms. And the reason why we have to do it is because atoms are so tiny. To have a reasonable quantity of them would, for us as people, means that we have, or like a useful quantity, would mean that we need a huge value of them. So remember, 1 mole is 6.02 times 10 to the 23rd atoms. 1 mole just means that. And when we talk about atoms, we'll use that. Sometimes we talk about molecules. It's the same value. that's there. Now, why can't we just use mass? Well, remember, each element is going to have a different number of protons and neutrons, and that's what gives mass to the atom. So this means that every element has a different mass. But in reactions or making solutions, we want to know more so the number of them, not necessarily the mass of them. So when we talk about the number of them, it'd be too hard to talk about like such huge quantities, because something times 10 to the 23rd, it starts losing meaning to us because it's just so gigantic. Humans can't comprehend that value, or how big that value is. So instead, we use the mole in order to discuss about how much we have in a reasonable way. We are going to use mass because mass is how we're able to measure it in the lab, but mole tells us how many there are. All right, so let's go over how we do some conversions with the mole and compounds. So just like we can convert using Avogadro's number between moles and atoms, we can do that with molecules. So let's solve one here. So how many moles are there in 9.34 times 10 to the 16 molecules of oxygen gas? So we're looking for moles, and we have 9.34 times 10 to the 16 molecules. The fact that it's oxygen gas doesn't matter, because we don't have to worry about the mass with this. When we're going from between moles and molecules, we just use Avogadro's number. So that's at 6.02 times 10 to the 23rd molecules per mole. And that's for every 1 mole. Unfortunately, there's no abbreviation for molecules. So when we're solving this, we're going to start with what we're given. So we have 9.34 times 10 to the 16 molecules. And we're solving for moles. So I'm going to put 1 mole on top. It's always a good bet that what you're looking for is on top, unless you have a split unit. And then I'm going to put molecules on bottom, so 6.02 times 10 to the 23rd molecules. And I'm doing that so that I can cancel those units. Remember, the value doesn't cancel, just the unit. So you plug that into your calculator, and you should get 1.55 times 10 to the negative 7 mole. Great. So now you give this one a try. How many molecules are there in 1.9 moles of lithium bromide? So you can pause here and solve for it. And when you're ready to see the answer, come back. All right. So you should have gotten 1.1 times 10 to the 24 molecules. If I could spell molecules. All right. Be sure that you put your conversion factor incorrectly. Here you wanted moles on bottom and molecules on top. Remember, always start with what you're given. All right. Now let's talk about molar mass for compounds. Do you remember what it is? It's the average atomic mass in grams per mole. So remember, if we look at a symbol on the periodic table here, the atomic weight is our average atomic mass. So for hydrogen, we say it has 1.008 grams of it for every 1 mole of it. So it gives us a way to measure it out. So how do we find this for a compound then? Well, we're just going to look at the individual elements and then add up their masses. So let's do that. So we want to know what the molar mass is of calcium chloride, CaCl2. So Ca, calcium, is 40.08. And chlorine, I have 2 of them, so I'm going to do 2 times the mass of chlorine, so it's 35.45. And then you add that all up, you plug into your calculator, and you get 110.98 grams per mole. The periodic table you get on the test goes to the hundredths place, and honestly, that's pretty much where you need to go. It's not really necessary to go any further than that, in this class at least. But I wouldn't recommend going any below that. So I would stick to the hundredths place, because if you round too soon, you might not round correctly, and that's going to cause, it's going to give you some incorrect value. So I would always go to the hundredths place. So let's have you give this a try here. What's the molar mass of dinitrogen tetraoxide? Again, pause here, solve it, and when you come back, I'll have the answer. All right, so you should have gotten about 92.01 grams per mole as your value. All right, so now let's talk about the math we do with that. So we use this then to convert between mass and moles. So let's solve a problem with it. How many moles are there in 32 grams of sodium nitrite? So the first thing we want to do with these problems is we want to find the molar mass. So we're given grams of sodium nitrite, we're looking for moles. When you're dealing with grams or mass in any way, we need the molar mass in order to do conversions. When it's just mass in moles, we don't worry about Avogadro's number. All right, so let's find the molar mass of sodium nitride. So sodium is 22.99. The mass of nitrogen is 14.01. And we have 2 oxygens with a mass of about 16, and you should get 69 grams per mole. All right, so now we're going to use that to convert to moles. We're going to start with what we're given, so 32 grams. And then I'm going to plug this in so that grams cancel. Remember, when you have a split unit, the value stays on top, or with the top unit, and then 1 goes with the bottom unit. So I'm going to put 69 grams on bottom and 1 mole on top, and that should be about 0.46 moles as your answer. All right, so let's have you give this a try here. How much copper 2 cyanide would you need to weigh out if you need 3 moles for a reaction? So again, pause here and solve it out, and when you come back, I'll provide the answer. All right, so you should have gotten 347 grams. Great. Compounds. Now we're going to talk about types of bonds here next. We have 3 main types we're going to look at this unit, and some next unit as well, or focus on some next unit. So this unit we're going to talk about ionic bonds, and we're going to spend a lot of time on ionic bonds. So with ionic bonds, we're transferring electrons. And what that means is, remember, ions are charged elements, or charged atoms. So what happens is sodium has 1 too many valence electrons, so it's going to give that electron over to chlorine because it wants 1 more. So now chlorine gets a negative charge and sodium gets a positive charge, and they're going to stay near each other and actually form these crystal structures based on that in order to balance those charges out, because while they're more stable, they still have charged them. So we're transferring electrons with ionic bonds. We're going to see them between metals and nonmetals. And so here we have that key here. So here we see a metal with a nonmetal. And they're going to form a neutral charge. That's going to be really important in this unit. So sodium chloride is an example of that, NaCl. Covalent bonds, we're going to spend a day on them this unit, but the whole next unit is actually going to be focused on them as well. So with covalent bonds, we're sharing electrons, and they're made of 2 nonmetals, as we see there. And they bond to fulfill the octet rule, and we'll talk about what that is, I think, next unit. And water would be an example of that. The last type is metallic bonds, and we'll spend a very brief lecture on those. And these have electrons that roam freely. They're only made of metal atoms, hence metallic bonds. And a gold bar would be an example of that. So like if we just had Au, solid gold, or iron. Alloys too, like alloy of metals, those would also be considered metallic bonds. Okay, so electronegativity is going to play a big part in what type of bond forms, so we need to go over it again. So electronegativity, this is going to be an atom's pull on electrons, and this is when it's bonded. So here we see oxygen is much more electronegative than hydrogen, so it's trying to take those electrons away. What's the periodic trend for it? It's going to increase up and to the right of the table. So if I were to draw out a periodic table here, remember down here it's going to have low electronegativity, and up here we're going to see a high electronegativity. This is with the exception of the noble gases. The noble gases have no electronegativity because they have no desire for more or less electrons. Metals, like we just said, are going to have a low electronegativity, and this is because they don't want more electrons. Remember, things like electronegativity and a lot of the periodic trends have to do with them getting those 8 valence electrons, and Metals just have one or two many more valence electrons, so it'd rather give up those electrons, so they're going to have a really low electronegativity. While nonmetals have a high electronegativity, and this is because they want more electrons. Remember, like, they're only getting one or two away from having eight valence electrons. So if they add more on, then they're going to be more stable. So they're going to have a high electronegativity because they have a high desire for electrons. Okay. Difference in electronegativity and bonding. So, and I'll talk about how to find that towards the end here. So when we look at difference in electronegativity, it can help us predict the type of bond and what properties it might have. Ionic compounds, we're going to see a large difference in electronegativity, and that's because it's a metal and a non-metal, right? And metals have low, non-metals have high, so it's going to be a large difference. And covalent compounds, we're going to be able to see if they're polar or non-polar. So let's talk about what that is. So remember, covalent compounds are, they're sharing electrons between atoms, but some aren't sharing equally. Non-polar bonds have a low difference in electronegativity, so the electrons are shared evenly. This means that the elements have an equal pool on the electrons that are being shared, and so those electrons aren't moving anywhere. They're going to be distributed equally between them. Polar bonds, though, have a large difference in electronegativity, so the electrons are shared unequally. So here, chlorine has a large electronegativity compared to hydrogen, so the difference is big. So that means chlorine is much stronger and pulling the electrons away, while hydrogen is weaker and barely holding on to those shared electrons. When we talk about covalent compounds next unit, we'll do a lot more in this and what it means. It just helps us with the next part here. So I'm using kind of vague terms, right? Large, small, all that. There are actually some numbers that we use. So here we see the bond type, and delta means difference, En referring to electronegativity, and so the ranges of them for those bond types, so the difference of electronegativity range. So ionic compounds, like I said, they have a large difference of electronegativity, so we're going to see that if the difference is greater than 1.7. Nonpolar covalent, these are going to have a small difference in electronegativity, and so we're going to see that when it's less than 0.3, and then polar covalence in the middle there. Now, these are going to give us an idea of what bonding is like, but they aren't actually set in stone. It's more of a spectrum. Some textbooks are going to give you slightly different values. So if you see like 0.5 or 1.4 as the cutoffs, it's not that big of a deal because it's a spectrum. And for some things, say it has like a difference of 1.6, it's going to be covalently bonded but have ionic characteristics. So for example, acids do this. So HCl, hydrochloric acid, that's a covalent bond. They're sharing those electrons. But when we put it in water, it separates out into their ion forms. So we see some compounds are going to have a variety of properties based on that difference of electronegativity. So how do we find this? Well, difference means subtract. So we're going to subtract their values. So we would look up the electronegativity for each element, then subtract them. And you want to view this as an absolute value calculation, so don't worry if putting one in front of the other. Just focus on the value itself. And so I don't expect you to memorize these values. You should know the trend, and you should know that chart we looked at here, so those values there, but I don't expect you to memorize like the individual values. But you should be able to solve for this. So let's do some. So let's look at calcium and chlorine. So if I look up carbon and chlorine. Oof. So carbon has a electronegativity of 2.5 and chlorine of 3.0. So remember, I'm viewing this as absolute value. So that gives me 0.5, and so then that would be polar. So now let's have you do this for lithium sulfide, or between lithium and sulfide, or sulfur. Ooh. All right. So you should have gotten 1.5. Now that's interesting, right? Because it's telling us based on that value that it'd be polar, but lithium's a metal, sulfur's a non-metal, that tells us that would be ionic. So this is what I'm talking about, those spectrums of trends, right? It's not a hard and fast things with difference in electronegativity. Right? So that is the end of chemical bonding. In the next videos, you'll be taking a look at ionic compounds.